I need to understand those minimums a little better on those plans and departure charts. I know we're going to go through some more of that stuff, but I just...
Yeah, we will for sure. So, okay, so we're going to start taking a look at the second half. Let me bring the stuff up here real quick. So the Phoenix Seattle is the one. If you guys have it handy, get that information out. Screen here. Garrett was asking me what days I'm moving, but I don't have any clue yet. Whenever someone buys my house. If not, I'll be commuting. Okay, so this is the Phoenix Seattle flight plan that we started. We started filling out some of this information, so let's just go figure out where we're at here. Okay, so we've got the route all in there. We did that initial fuel. So yeah, all this stuff is still blank. We picked all of our runways for takeoff, landing, the instrument approaches, filled in all of the minimums and everything already. We did the weight and balance. Everything looked good there. We've got it all plotted on here. So, okay, so we should be good. So we estimated on this flight, our initial fuel estimate came up as 14,400 pounds of fuel. That was via using that 4,000 pounds first hour, 3,000 pounds second hour estimation that you guys have been doing all week. Okay, so now we're going to introduce the next little part of this, which is called the simplified fuel estimate that we're going to take a look at. So let me bring up the charts for that real quick. So now we're going to start taking a look at some of the different charts we use for the CRJ 700 flight planning. I'm going to drag these over into here. Okay, so this is a little packet of the primary charts that we end up using. So you're going to have to, I'm going to walk you through kind of how we start using some of these things. So obviously you're going to have to reference back to this video. And obviously this is all recording here. So we're looking first for what's called the simplified flight planning charts, okay? And they're just a few pages in from the beginning here. The first couple of pages are all altitude selection charts on how we select our altitude. Actually, let me go back because actually we do need to figure out our altitude at the very beginning here. Okay, so we'll just actually start with the beginning, so we don't need to read that part. So that's altitude selection, short distance, altitude selection. So this right here is an altitude selection chart. As we go through this part of the section, there's a couple of different conversions that you guys are going to learn how to use with temperature. Okay, so when we start looking at this is kind of ultimately this is a chart that is going to give us an additional idea. Like so far we used that 4,000, 3,000, 4,000, 4,000. So we use that first. Okay, that's, as you can tell and as you would think, like obviously in the real world we don't use such a just ridiculous estimation in real world aviation. So basically what we do in here is there's 3 different ways that we basically estimate our fuel. We do that. The first thing we do is that one we've already done, you guys have already learned, that's the initial fuel estimation. And that really, the only reason we even do that one is just to get us a rough idea of what our fuel will be. And if anything, it's kind of an overestimation, okay? So it's, if anything, it's going to put us a little on the heavier side than more fuel than we actually really need. And then as we do the next one, we do this next one, which is called the simplified fuel. That's going to refine it down a little bit better for us and kind of give us a little bit more of an accurate depiction. This one is going to take into account the temperatures that we're going to be flying, like we're going to be taking off in, landing in, and flying through, and then also the winds along our entire route. Okay? So the first thing we need to do, and what we're going to show is we're going to talk about this little thing here. As you can see these little lines up here, you see this term in here. It says ISA plus 20 degrees, ISA plus 15 degrees, ISA plus 10 degrees. So has anyone ever heard the term ISA yet? In here, right? So if you go all the way back to like quiz 1, 2, somewhere in there, we talked about ISA. So however, I don't necessarily expect you to recall it because it was weeks ago now and there's been a plethora of information since then. But ISA, so you're going to start seeing, and you probably already have seen, we're going to start taking stuff that we've learned and we're basically kind of now bringing it back in and putting it into practical use, showing you why we learned it and where we're applying it. So ISA is the International Standard Atmosphere. Okay, and what it means is it basically says to us that at sea level, if we're at sea level, the temperature should be 15 degrees Celsius. Okay, so this is just kind of more of, an overall general idea that I don't know how they came up with this temperature or whatever, but it's what we use ultimately to figure out how we do performance and what charts and things we look at. Everything in aviation, temperature-wise, is based on ISA, okay? So ISA assumes, I should say, the best way to phrase it is that ISA assumes that we're at sea level and it's 15 degrees Celsius, kind of as our starting point, okay? That is what ISA equals, 15 degrees Celsius at mean sea level. That was one of your quiz answers way back when, right? So with ISA, the thing about ISA is, although we assume that we're at sea level and 15 degrees Celsius, rarely in the real world are we ever at sea level and at that exact temperature. So what we do with this ISA figure is we take wherever we are at and we have to compare it against ISA. That's kind of what we ultimately do. So I'm going to pull the weather packet back up that we are using for the Phoenix Seattle flight that we're doing here. Where to put it. In here and just grab it because we wrote down the information in here. Okay, so we're going to take a look at Phoenix first. So Phoenix, we wrote down the weather that we can expect at departure in Phoenix right here, right? So this is our temperature. This is basically the current weather in Phoenix. It shows that it is 31 degrees Celsius, okay? So ultimately what we're doing here is we are taking this temperature, this is our origin, and what I like to do during this part is we kind of break down the route because we start gathering different temperatures kind of in this phase to come up with some averages for our flight so that we can use it on our charts. So the first thing we look at is we look at Phoenix, and we see that it is 31 degrees Celsius. So in order to figure out this whole thing about ISA is we have to figure out, one, what our temperature is currently, and then we have to figure out, we have to go and take a look at the elevation of Phoenix. So let me zoom out here, go back to the high chart, go down to Phoenix. That's Phoenix. So I'm just going to bring up the airport here. So when you go into Phoenix, when you bring up the chart, right here on this chart, it'll always tell you the elevation right here. Surveyed elevation, 1,134 feet above sea level. So what we're basically doing here is we're figuring out, we're doing this ISA comparison. So we know that ISA is 15 degrees Celsius at sea level, and now we're looking, okay, well, what are we? We're starting this flight in Phoenix on the ground, and on the ground in Phoenix, we are sitting at 31 degrees Celsius at 1,134 feet above sea level. So now what we have to figure out is what is our difference between what we currently have as our real world condition and what ISA assumes that we always are supposed to be, right? So do you remember when we were talking about the temperature lapse rate? It's part of the ISA theory stuff. So if you're at 15 degrees Celsius at sea level, every 1,000 feet that you start increasing in elevation, we assume that the temperature decreases by 2 degrees. So if you're at sea level, it's 15. If you go up 1,000 feet to 1,000 feet above sea level, it should be 13, and so on and so forth. You keep going up, you can start kind of doing your math. 2 degrees for every 1,000 feet. So based on the ISA assumptions, if we're at 1,000 feet above sea level, which is Phoenix is slightly above 1,000 feet, so 1,134 feet. But if we're following the ISA principle, it should be 13 degrees Celsius at 1,000 feet if it's following the ISA standards, right? Well, clearly we are we're at 31 degrees in Phoenix. We are way above ISA. Okay, so what we need to do is we have to figure out how far off of ISA we are sitting. And these numbers that when we look at this, this is where you'll start seeing a lot of charts that we use are called ISA. You'll see a chart that says ISA temperatures, and then you'll see one that says ISA +5, ISA +10, ISA +15, ISA +20. So we need to figure out where we are as compared to ISA. So if it's supposed to be 13, and we know we're a little bit above, but when you only go 2 degrees per 1,000 feet, even if you're at 1134, it still technically is going to be 13, right? So we're at 31. So 31 minus 13. What's our difference between ISA?
18.
18, is that what it is? So we are sitting at ISA plus 18. That's basically what Phoenix currently is. It's taken into consideration with the elevation and what ISA should be, okay? So it should be, at 1,000 feet, it should be 13, but we are really at 31. So we are 18 degrees warmer than what it should be as to what ISA says it should be, right? So ISA plus 18. So when we use that, we can write down. So when I'm doing my flight plans, I kind of keep a piece of scratch paper, and I keep all of these, these little notes. Like I'll do a little note section for my origin weather and like origin information, essentially, en route information, and then destination information. So I would normally write this little number down for my Phoenix origin information. I want to know what my ISA number is, and I'm sitting at ISA plus 18. That's what we're at in Phoenix for this flight. And the reason we want to know that is because once we go and start diving into the charts, we need to know how far, what chart to use. So when we start looking at charts, if you're at ISA plus 18 for your temperature, then we always, remember kind of the little common thing in aviation and planning, we always penalize it more than what it really is. So you have two choices. You can either use ISA plus 15 or ISA plus 20. In aircraft performance, hotter is always more penalizing. Okay, so if we always go above what it is. So if we're at 18, we always round up. Just like the ceiling thing. If it's 401 feet, we round it to 500. So it's kind of like that theory where we always make it worse, So when we start looking at charts, we know that we are going to round up. It's got to be, if there's not a chart for ISA plus 18 right on the nose. So they always just go every 5. So plus 15, plus 20. So we're going to end up using ISA plus 20 as our temperature number. Okay, so we figured that part of it out for Phoenix. I'm going to come back over here. So this chart here that we're looking at, and they kind of look confusing at the beginning, but ultimately the charts are pretty easy to use. Let's zoom back in on this one here. So you can see these little lines right here. ISA plus 20, ISA plus 15, ISA plus 10 degrees Celsius and below. These numbers on the left over here are our altitude. Flight level 410, so 41,000 feet, 39,000, 37,000. So what this chart is helping us figure out is what our aircraft is going to be capable of climbing to. So there's 3 things that we need to know. There were 2 things that we need to know essentially for this chart. We need to know how much our takeoff weight is, which we already know. We've done our weight and balance. And then we need to know what our origin temperature is. Okay, so let's cruise back over here really quick and go back to our weight and balance. Our takeoff weight, 74,404 pounds. And then we already know that ISA number. We're at ISA plus 20. This is going to tell us how high is this plane going to be able to climb up to. So we're figuring out what our cruising altitude is going to be for this flight. That's what we're doing right here. So we're clear up here, 74,400. So that's 74, that's 76. We're basically at 74,500. So we're going to round it up, nearest 100, but going up always. So we're going to be right over there. I'm going to put in a line. And then we're also on this ISA plus 20 line. Okay? So we have to basically just draw a line here that meets up from here, wherever it meets into this line, and that's going to be our altitude capability for this flight, the max that we'll be able to climb. When it's hot, it's always harder to reach the higher altitudes. So I'm going to draw a line from basically the middle here. Just go straight up. Just wherever it meets this line, basically right there. That's going to tell us. So I mean, it basically, lucky for us, it hits it basically right at 35,000 feet. So the next consideration for this, so we know that we cannot climb any higher than 35,000 feet for this flight. The next consideration for us is, what direction are we flying? We're going Phoenix to Seattle, but overall, and when I say direction, what I ultimately mean here is, because we're looking at which flight level we're going to file, as far as, if you're going east, we do odd levels. If you're going west, we do even levels. So you have to base this off of, even though most of this flight is like northwest, technically that's going to be your real direction, is it's northwest. But if your origin, in a situation where you're going like kind of, straight, and I'm doing it the way I'm looking, but if you're going this direction, Phoenix to Seattle, northwest, if your destination, you just need to figure out, is my destination west or east of where I took off from? It's wherever you end up. That's kind of how you base what you're going to file, as far as, okay, this flight overall is a western heading flight or an eastern heading flight. For the most part, it's mostly north and then west. But so Seattle is west of Phoenix, is ultimately what I'm getting at. So we are going to pick west is going to be the main heading of this flight, and because we are going west, this flight has to be filed at an even flight level. So anytime we go west, it's even, and east is odd. They have like a little acronym for that. It's called NEOD Sweven. Has anyone ever heard that? So it technically means north and east is odd, and then south and west is even. So anyway, NEOD Sweven, in case you want to remember that. But really, if you the best way is just to say, well, is my destination west or east? Because you might be on a flight plan that circles over here, and then if you go around weather, then you're going east for a while. But wherever you end up landing, is it east or west of where you took off from? That's really how you're going to base this. That's the best way ultimately to look at this. So Seattle, obviously west of Seattle or west of Phoenix, so we're going to file it at an even level, which means this right here, the cap on our altitude is 35,000 feet, which means that we have to take this down to 34,000 feet in order to comply. So you don't go in between. You always go to an even, to the nearest 1,000, and then you basically adjust it from there. So we're going to end up filing this flight at 34,000 feet, even though our capability is 35. The problem is in order to get higher than the 35 or to go up, we'd have to be able to have the capability of hitting 36 in order to, go any higher than 34. That's the problem, is because if you're going west, you got to stay on an even level, and you can't go to 35 because that's for people going east only. So that's how they do a lot of the separation of traffic. They're always at odd and even altitude levels. So we know, so this flight's going to be filed at 34,000 feet. And we're ISA plus 20 in Phoenix. So now we've got that part of it figured out, 34,000 feet. Okay, the next part that we are going to figure out, I need to input the flight plan back into SkyVector. Somebody want to read it off to me because it cleared it out when we were doing the last class.
Yeah, I took notes, but I didn't write down any of this flight, so I'm sorry.
You got it on your.
I've got it on my thing over here.
All right, I got Zephyr, Chili 14, BTY, J92, Klamath, J189, Battleground, OLM.
Okay, so what was, sorry, can you do it one more time?
Yep, Zephyr.
So Z-E-P-H.
P-E-R. Nope, P-E-R. Or, oh, maybe I spelled it wrong. That could be it. Zephyr to Chili 4.
Was it like that?
That's what I have written down.
Okay. Well, that was, yeah, because that was an intersection, and then to...
Chili 4.
This is the one that we had to put in each individual one, right?
Yeah.
Okay. So, and this is going to be a little bit tougher here. Hold on one second. I'm going to bring up our actual charts here. Skip. Oh, right there. Okay, so Zephyr, Carlo, Chili, Ramsey, Sissy, Dovey, Beatty. Okay.
We didn't have to put Carlo, did we?
You have to list everyone that's on there. I mean, it's the problem is with the SID is that if you're looking at it like this, I know it looks like, let's see, where was Carlo? Like right here. It looks like, it just goes straight through it because you're going to Chile.
Yeah.
But a lot of times, most cases, it really wouldn't make a difference. But there's several SIDs or stars out there where if you're having to do it this way and you don't put in every point, you're gonna get the one that it really is not right on the route, where it ends up being like a different distance. So
we only had to do this because
SkyVector wouldn't take the SID.
Okay.
That is the only reason. Yep. As far as the way we wrote it out on the plan, we don't even write it like this. So.
What does ALS stand for?
Approach lighting system. Hello, Chili. And it was Ramsey, Sissy, Dovey, Beatty. Okay. Then from that point, what, J94? 92 to Klamath to Battleground. Where's he? No, Klamath.
J189.
Then J189 to Battleground, and then OLM too.
Yep.
Okay. All right. Okay, so that puts the route back in there. So going back to kind of where we just left off a second ago, for some reason that's not following that. So hold on one second. What's that? Okay. J92. Okay. So that should put the route back in there. So we're filing this route 34,000 feet. We've got the route back input in there that we had from before. It is 1,048.5 miles is the total distance. Based on a speed of 400, it's 3 hours and 42 minutes. So we know we're going to be at 34,000 feet. The next part that we have to go figure out is we have to start gathering the overall wind information for this route. The wind normally is going to be just in your weather packets that you get from me, okay? It'll be, what we're looking for right now is the winds aloft data, and that's going to be basically different random, it's going to be different weather, like wind reporting stations that are along our route. So if you go back to this, back onto this, our flight plan packet here, this page here where we put in where this map is in here. Now, this map, whether you use it or not, one thing that it is useful for to take a look at is that all of these, so if you see how it has all of these different little stations in here, some of these are airports, some of them, are VORs, but basically ultimately what all of these represent the winds aloft reporting stations. So the one thing that's nice when you're looking at this is if now we don't have our route on here, but if you wanted to like pencil in kind of where your route goes, you could go Phoenix and then kind of draw it up and over to Beatty and then up to Klamath and up to Battleground and then up to Seattle. So most of those points will be on here. You don't have to have it exact as we have it like on SkyVector. That's where we use the exacts to get the measurements and stuff. But on here, this is telling us where the wind reporting stations are along the route. The thing about the wind reporting stations is not every airport and not every station will have winds, okay? And when I say winds aloft, it means like the winds up in the upper atmosphere, like talking like, once you get like 10,000, 12,000, 14,000, 20,000 feet, 25,000, 30,000, up into those higher, really high altitudes, it's going to tell us what the wind speed is at that altitude and the temperature is at that altitude. Those are things that are very key ingredients for our flight planning process. Because we can look at METARs and things like that, but that's only telling us what the temperature is on the ground. When we're flying through the air, we need to know, along this route that we just created, we need to know what the temperature is at 34,000 feet above Las Vegas. Because we're going to we kind of go right over Las Vegas. We go right over Beatty, right here. So we need to know what those temperatures and wind speeds are at that altitude over, Beatty, different points along our route. But basically, we want to use those wind reporting stations that are closest to our route. A lot of times you're going to find that you don't necessarily have wind reporting stations that are right smack dab on your route, and that's pretty common, but we just find the one that's nearest and just use it. So when we start looking at this, you've got Phoenix, that's where we're starting. You can see that we've got a couple of them right in this area of northwest Arizona. You've got one over Vegas, you've got one over Beatty, one over Coaldale, one over Reno. You get up into here, you've got one over Lakeview, one over Medford, Eugene, Portland, Seattle. So we have several that are going to be very useful for us along this route. So I'm going to go in and I'm going to get our winds aloft data. You don't need to worry about where I go get this from, because I'll always just copy and paste this into your weather packets for you guys. So let me pull it up.
Did you hear back about the electronics and the practical test?
Not from the FAA guy, no. But ultimately, the more I started talking about it with Greg, the more, as far as all of the information that you have on the Google Drive, we can just create an offline version of that, which you'll just be able to use with a computer. The only real question out of that entire electronic thing is just simply the whether you have to find your flight plan on SkyVector or using those. So at the end of the day, we're talking a difference of maybe 10 to 15 total minutes of whether you're able to save 10 or 15 minutes by doing it on SkyVector, or whether it takes you 10 or 15 minutes longer because you had to whip those out. But as far as anything else in the entire process of the practical, nothing else would be different. So the whole thing is just having an internet connection. Unless we have a way of figuring out a way of creating an offline version of SkyVector, that would be the only answer to that. So that seems like it's the only thing that we can't necessarily get around. So we'll just plan on using the charts, which you'll have there available for you. And we'll even use them if you want. On the next couple of flight plans, we'll use the paper charts, and we'll just omit SkyVector, and you'll see the difference. I mean, the only thing, the SkyVector is a convenience, but it's not changing necessarily one thing that you look at. The only thing it's changing is that instead of it being on the table, spread out, it's on your computer screen condensed.
And it calculates our distance.
Yeah, calculates your distance, but kind of as we looked at it last time, that distance part, when you take those big sections and just add them all together, and then the SIDS and stars will give you the total distance from the airport to the transitions, whatever one you choose, you can just get them right there, add that all in. I mean,
But is that at the 400 speed on the charts?
distance not based on speed at all. So, yeah. You need to know what the total distance is, but that has no bearing on your speed. So that part won't make any difference. As soon as you add up your total distance, then you just calculate whatever speed you want the same way you already do it. Instead of SkyVector calculating it for you, you're just going to take, well, if I'm 1,048, like on this one, and I want that initial 400 speed to kind of get that initial ETA, then you just have to, instead of it telling you, you're just going to have to take 1,048 divided by 400 and just get it. So, but
Use a calculator for this.
yeah, you can use a calculator. You can use flight computer. When a flight computer is the thing that helps calculate the fuel burns. Were you here? Were you here when we were talking about that? You weren't here last time, right? So when her class went through it, I always gave them the kind of the caution, right? That there's a chance that you could end up having to use paper charts because it was always a chance. If the, in the practical, they knew that they might have to, right? Nobody had to so far, but in going back to a lot of my previous classes and when I taught at Salt Lake Community College, it happened more often then, but it was basically just saying you might not be able to use Sky Vector, and now it's really more of a more for sure. There's a slight possibility we might be able to use Sky Vector, but most likely not. They just changed the rule last week that says that you're not allowed to have a device with an internet connection. So the only information further than that we've been given is that if it's something, because we're allowed to use certain things that don't have an internet connection, like the flight computer stuff and whatever. If it's any materials needed for the class, it just has to be on a device that's not connected to the internet. So if it was, you can actually, on all of your guys' devices, if you go into the Google Drive that you have access to, you can just hit the download button and save an offline copy right on your device. That'll take care of that, because once you go, if you're taking your practical, he's just going to make sure you're not connected to Wi-Fi or whatever. So the only question from that point, and if we can figure out a way of making Sky Vector work not connected to the internet, then we're fine. It's just really the internet connection, because they don't really care that we're using the computer to do the flight plan. It's just that, and I don't know why they care about this, because the examiner sits there and watches you the entire time. And so if you're sitting there Googling stuff, he's going to see you. And honestly, even if you had access to that in the first place, which we always have in the past, there's no way to Google your way through any of this. It's not going to help you one bit, even if you do have an internet connection. So I never understood the theory of it, but anyway, it is what it is.
Do you have a preferred flight calculator? Computer?
I don't. I've always had ones downloaded on my thing. So the thing is you can just get a free one. Did you get one? What was the one you got? Mine was E6B something.
Oh, you can use an E6B?
Yeah, absolutely. Yeah, that's a flight computer. E6B is a flight computer. So
We're gonna be able to use the app on our phones, or we're gonna
yeah, you just have to turn your internet connection off, or turn off your cellular service data, whatever. Yeah, you can use that offline. You can use your laptop or tablet to access the Google stuff. Just need to save an offline copy. Really, the only question is just the Sky Vector, if we can figure out a way to make that work. If not, then if you think about it, the Sky Vector is just that part. I mean, once you get done through all of this, you're going to realize how insignificant the Sky Vector part is. Right now it seems like a big part because we're only to this part, essentially, or through this part, and that's the part you've been working on. But once we get done through the rest of this stuff and the fuel burns, you're going to realize that the Sky Vector portion is really insignificant. It does help you with the math. It is convenient to not have to add up your whole distance, but honestly, it's basic math, and it takes an extra couple minutes to do it. That's really the truth at the end of it. So, and obviously it allows me to show that online up here. It's probably more help to me than it is you. So we need to, winds aloft. So give me just 1 second here. I'm going to go in and get all of our information that we need here. It's Vegas, it's Phoenix, Vegas, Beatty, Coldell. Sorry, this takes just a second to do. Okay. Oops. So do you guys remember looking at wins aloft data back once again also at the kind of the beginning of class? Okay. Well, here's a quick recap of how it works. So I pulled Phoenix, Vegas, Reno, Lakeview, Portland, and Seattle for our wins aloft data. Like I said, I'll always give this to you on your flight plans just like this. I'll go in and I will pre-select the ones that you're most likely going to use for you and just give them to you just like you see right here. So we've got each station. So this is listed in order of how we are going to fly the route. So first we start in Phoenix. This right here is saying 3,000 feet above Phoenix, 6,000 feet above Phoenix, 9,000, 12,000, 18,000. 34 or 24,000, 30,000, all the way up to 39,000 feet. A few things on here. When you are at 24,000 feet or below, you'll notice that there is either a plus or a minus symbol in all of these readings in here. Okay, that simply is just meaning that the temperature is either negative or positive. So like right here, at 9,000 feet above Phoenix, these last two digits here, and we'll run through how, we're looking at how we read these, but it's just saying that the temperature is plus 12, but 12 above. Once you get to 24,000 feet, anything above 24,000 feet, it doesn't have that symbol in there because every temperature is negative, no matter what. Okay? So when we're looking at all of these different readings here, so we'll just look at Phoenix. At 3,000 feet, let's see, actually we'll just start with 6,000 feet. So at 6,000 feet above Phoenix, now remember, this is always mean sea level, these readings here, okay? So Phoenix is at 1,100 feet above sea level, but at 6,000 feet above sea level, right over Phoenix, the wind is 190, so coming from 190 at 14 knots. So when we look at these readings, the first two digits, and you may, if you didn't have it down from the first time we looked at it in class, you may want to write this down. The first 2 digits is where the wind is coming from. Kind of like when you're looking at your METARs, right? In a METAR, the only difference is it's going to usually give you 3 digits. In a winds aloft reading, it's only going to give you 2. So it's always going to be to the nearest 10, no matter what, because of it only being 2. So on the first one, you always add a 0. So you take the 19 and you add a 0, okay? Regardless of what it says. So the wind, in this case, is coming from 190. The next part is going to be the 2-digit speed. So it's going to be just exactly what it says. So it's going to be 14. Oh, did I just delete that? Oh, crap.
Just hit the back button up in the top left corner. Once more.
Okay. So it's 14 is the speed, and then the next two is going to be the temperature. So it's plus 20 degrees Celsius at 6,000 feet. So you can jump to 9,000 feet. The wind is coming from 200 at 26 knots. Temperature is plus 12 degrees Celsius. Okay, keep going. 12,000 feet. Wind is still at 200, 25 knots. Temperature is now plus 7 degrees Celsius. 18,000 feet. The wind's coming from 210 at 33 knots. But now it's negative 8 degrees Celsius. 24,000, 220, 39 knots, negative 20 degrees Celsius. Now that we're above 24, everything now is assumed just to be negative from here on out. But 30,000 feet, the wind is from 230 at 66 knots, and negative 33 degrees is the temperature. At 340, 230 is your wind direction. 79 knots is your speed, and negative 42 is your temperature. And then 39,000, 230, 95 knots is the speed, negative 52 on the temperature. Okay, so that's how these are read. Now, this is a good one to have up because it also has some other clarifications on here, like other types of speed. So if you see, let's see here. Another one. So let's first look over here. So if you go to Lakeview, you'll notice that there's not a reading at 6,000 feet. Okay, if you see it missing a reading, it's simply because the station that's reporting the weather is at or above that elevation. Okay, so like for instance, like if you're looking at Denver, which is a mile high, right? It's not going to have a reading for 3,000 feet above sea level because it's already above 3,000 feet above sea level. So if you see the report missing, that's just simply because it's within a certain proximity of the ground already. It's not, not readable essentially. The next one I'm looking for here. If you see like this, if you see I don't know why it said that, 9900, that just means that the winds are calm. It's kind of weird because the thing is if you take the 2-digit speed, right, you can't have wind from 990. It's because you only go up to 360 degrees. So you can't have wind from 990. And then the next one is it's 00 on your actual speed right here. So that's just the 99 is to signify calm winds. So if you see a 99, because otherwise it doesn't make any sense, right? You can't have wind from 990 at 00 knots. So, but it does give us the temperature, which is negative 47, but otherwise it means the wind is calm. So when you see that, just know that means it's calm winds. So we don't plan anything, just 0.
Give these numbers. They put the balloons up and do all that. Is that where this is coming from?
Yeah, weather balloons primarily. It's a mix of weather balloons and then actual aircraft data that's flying over, up above. So this is probably the least out of all weather products that we have available to us. Winds aloft are the least accurate because we have the least amount of, good tools to actually read these. So, but yeah, most of it is just, the weather balloon stuff, letting it go every morning or every 6 hours or whatever they do. What?
What about the one on Reno where there's no temperature?
That one right there?
Yeah, that one.
In this case, it's because, sorry, just need to leave it alone. So when you don't, like this one doesn't have a temperature, and then also this one above Phoenix doesn't have a temperature, right? So when you see that, it's just simply if it's 3,000 feet or less from where the station is. So like for instance, Reno is pretty high elevation. It's like close to 6,000 feet, I believe. But if that level is actually close enough, if it's within 3,000 feet of what the actual station elevation is, then you just use the default of the station at whatever the temperature is on the METAR. Does that make sense?
Yeah.
So like we know that Phoenix is 1134 on the elevation, right? So because this is 3,000 feet, it's less than, technically it's within 2,000 feet of what the actual elevation is of Phoenix. So we just would use the METAR temperature on that one. So you have to get more than 3,000 feet outside of the whatever the station is in order for it to give you the actual readings. And it's the same thing on like Lakeview. If it's within a certain amount, like if it's within 3,000, it doesn't give you the temperature. And then I think if it's within 2,000 or within 1,000 feet of the ground, it doesn't even give you the wind. You just go off of what the METAR says. So Lakeview might be like at 5,200 feet, but because it's under 1,000 from what this is, that's why it doesn't list it at all, because it just expects you to use the METAR. Now, most of these lower altitudes we don't use anyway. So the only thing that we really care about is really the level, the altitude that we're going to be flying at. That's the only one that we're really concerned with. So what we want to do here is part of this simplified fuel planning process is we need to figure out the average wind for our entire flight, just as a whole average, okay? So what we do is we take all of these winds, and we're going to take all of these. So we know that we're flying at 34,000 feet. And luckily, this kind of works out good for us, because if you're flying at 36,000 feet or somewhere in between this, then you kind of have to end up interpolating a little bit between the two. You have to average it this way and then average it this way. So this works out good for us because we've got the exact 34,000 feet readings. Yeah. Great. Can you guys online still see those winds aloft? They can see them. For some reason it disappeared on us, so I might have to reset this for a second here. So I realized the problem of when it doesn't, like how at the beginning we were having problems where I couldn't get it to connect. If I'm logged into the GoToMeeting, it won't connect to this. So I always have to connect to the TV before the GoToMeeting. So now that it's disconnected.
Can we take a quick break while you're doing this?
Yeah, we'll take a quick break for a minute. I might have to actually look at that. Oh, it's not still working, but. Yeah, we're gonna take a break for like 10 minutes real quick, and then we'll come back to this in just a second. Yeah, it is a lot easier using SkyVector. Not a lot, but it's just giving you your, it's anything on the computer is easier. That's the bottom line. So.
It's just funny because you guys use SkyVector at work, don't you?
No, we don't.
You don't?
We do, but we don't.
Use something else?
It's not an official source of being able to use it. Like, you couldn't officially use it, but I still use it because I know it is accurate, but it's not. When you get into dispatch, everything you use for your planning has to be approved by the FAA. SkyVector is not an FAA approved source.
But there's a program, I guess, that is.
Yeah, there is.
I don't want to use that one.
Well, like on this, you mean? Like,
yeah, like when we take practical, you'd think they'd let us use the program that you guys use?
No, because there's no way to access it. I mean, yeah, you're talking, you'd have to. You'd have to subscribe to, get a license for WSI or Fusion and all of the stuff that they use. So, anyway, so going back to the winds aloft. So we need to average all of these winds aloft right here along this portion of the route. We're going to take all of these and we're going to get an average for this entire route. And we'll just kind of put our findings down here. So the first thing we want to do is let's average our wind direction. Okay? So if somebody doesn't mind jotting down these numbers, or if somebody has a calculator handy or whatever, we want to add up 230, 230, 240, 40, 70, and 80, and then divide it by 6.
148.3.
So 148,
Yeah.
if we take off the decimal, 148. Okay, so we could, and if we round that up to the nearest 10, we'll just take it to 150, because the wind readings are all to the nearest 10 on these ones. So. Okay, so the average wind heading is 150 for the average for the entire flight.
You added them all up and divided by 2.
Yeah, just the basic rule of averages. Add everything up, divide it by how many units you have. Okay, now let's take the next thing here. 79 plus 80, so we're doing the wind speed. 79 plus 82 plus 24 plus 28 plus 25 plus 77 divided by 6.
250.83.
Seems a little high. 250?
Yeah.
Just do 79, because it's got to be lower than 82. Yeah. So.
Okay, so 79.
Plus 82. Plus 24. Plus 28. Plus 25. Plus 77.
Oh, sorry, 52.5. I did the first time.
Yeah, well, those are easy to mess up on. 52.5, okay. So we're 150, we'll call it 53 knots. Okay. We don't really need to mess with the temperature at this point, because the temperature we usually isolate down to more of our origin and destination. So we already figured out Phoenix was ISA plus 20 for our takeoff. So our average wind for this flight is 150 at 53 knots. So that's what we're going to use for this simplified fuel. Okay. So now the next thing that we need to figure out is hopefully this will all save. we want to figure out what the average heading for this flight is. Okay, so what the easiest way to get the average heading, and I normally grab this at the very beginning when we start our route, but if you just delete everything in there and take it back to where it's just direct like that, that's going to be your average heading. So that's 322.
So how do we find that on chart?
On a chart, the easiest thing, so this isn't like an exact science when you're looking at this. I mean, like I said, this is another part that, that this will just give you when you look at it. But what I do normally, and what I did like when I did my practical, is I just look at this and I look at where Seattle is, and I just guesstimate that. So if I'm guesstimating that, I'm probably thinking 320 just by looking at it. So
there's no way to figure this out?
Well, the thing is you don't have to have it down to like the exact degree. It's not going to make, like you're talking like the difference on these degrees isn't going to make any difference on your fuel. You just have to have generally the right direction, probably within a 10-degree margin of error, worst case scenario, if you wanted to take, all you'd have to do is if you got onto the chart and went into Phoenix, and if you know your route goes a certain direction, you can just start looking at the actual radials that go out. Like that one right there is 330. Like you're not going to have this line in here, but if you know that your route, goes up and, goes to Chile intersection, you can look at that and eyeball that just right there. Because if you know if that's 330 and you're heading up through Chile, which we know is on our route, then you can look at that, guesstimate that. Any part of your route, you can look at the different radials.
One thing you can do is if you're doing it on like hard copy paper, you can take the edge of the paper, the straight edge, fold it over so that it matches up and draws a straight line from Phoenix to Seattle, and then read the VOR radial.
Yeah. Yeah, that's true.
Move the paper a little bit more so you can maintain the same VOR radial, but you can't read it when you're crowded.
When you do your flight plan, you'll have one of these in there, so you can also use this.
It's useless?
No, you can also,
use this. They'll give you one of these, but it's useless.
Yes. So I'm holding up a ruler thing that's used to do, so anyway, this will turn and it'll find it for you. You just match the line up. Anyway.
Perfect.
All of the stuff in my bag will be there for you. Okay.
Do you have the E60?
Yeah.
So
The manual one.
Oh my god.
Flight computer. See that? Sorry, you guys online can't see this. Actually, you can see it.
Don't worry, you don't want to see it. It's just too much math.
they're actually really neat and really easy to use.
But they're still math.
But
You guys see that?
It's like it literally is a calculator.
Cool. That's what we're looking at. The other thing that I showed them that you'll be able to use is this. This will find your degrees for you when you draw a line. Your heading.
Okay, so how do we use that?
Okay. Well, like John was just saying, if you just draw the line to find your average heading, you can just draw the line like that, and you can just simply use this. If you just set it right on Phoenix, you can just match it up with your line, and it's going to tell you exactly what it is. So that is what
not that part. Like what do we need this for?
What do we need that for? Okay. Well, I guess I was confused on what you were asking.
Sorry.
Okay, so 322. We'll just say it's 320. Okay. So going back to this, Average wind is 150 at 53 knots, and our average heading for this flight is 320 degrees. So now we need to figure out if we're flying on an average of 320, we need to figure out what 150 means to us. Like that wind, is it a headwind? Is it a tailwind? Is it a crosswind? We need to figure out how it's affecting our flight. Is it slowing us down? Is it speeding us up? We need to figure out what it's going to do to that speed, okay? So, because that's ultimately what's going to make the fuel burn more or burn less if it's a tailwind.
Gotcha.
Okay, so what I'm going to show you now is going to boggle your minds even more initially. Let me get my pencil out. I know Garrett knows how to do this really well. Not too worried about him, but I will turn on the camera as well so that everyone else can see. Now, one thing about this though, okay? So this is the manual E6B, okay? This is the thing that I just showed you guys on the camera a minute ago. Not the ruler thing, but this is the first thing I showed you. This is where you can actually get the app on your phone, and you can use an app and just download it. Just search for a free E6B calculator, or just even type in flight calculator into like your app store, your Google Play Store, whatever you use, and you'll find one. Just download it. But there are some that you want to kind of maybe look through those a little bit, and maybe try a few different ones, because some are better than others. If it's one you pay for, it's probably better. But if you don't want to pay for one, I found plenty of good free ones. But maybe, what was the one you used, Christy?
It just says E6B plus.
E6B, and you have Android or iPhone?
Android.
Okay, so E6B plus, if you got Android. I just got a new phone, so I had an Android, so I can't even remember the one that I used was. But what I'm showing you, or what I'm about to show you on this, can be done on that. Okay, so you're not going to necessarily end up having to use this in class. But if you do, you'll at least know how to use it. Okay, so if everybody wants to come up here and gather around, this will be the easiest thing. I'm going to turn on the webcam and attempt to hold this thing under. Okay. Like that. Okay. You guys see that good? I can't see if you're typing either, so you're going to have to turn on and say yes.
Yes. Yes.
Cool. Okay, so I'm gonna basically what I'm gonna do is I'm gonna show these guys, so you guys might not be able to see it that great initially, but then I will redo it like closer in so you guys can see it. Okay, so what we're gonna do is you initially want to just set, so this little circle here that's in the middle, this little dot, you want to set this just, it can really be on any of these speeds, but the easiest is just to put it right in the middle. It just happens to be 400 on this chart here. So that's just, the only thing that we really care about here is that it's just on an even number. And if you have it to like on a one, like on something that ends in 00, that's going to be the easiest thing to set it on. So this is 400, but the actual speed of what it says is really insignificant for what we're trying to do, other than just it puts it on kind of an even line for you to calculate with. So, okay, so the very first thing that we do is we're going to mark our winds, okay? So our wind speed was 150 at 53 knots. So what we do is we take this spinning thing, and this is going to be the top. This is a little marker at the top here is what we're going to align it with. You're going to take this to 150. So that is where our wind is coming from, okay, 150. Now the next part that we're going to do is we're going to mark where, like, our amount of our wind speed, which we're doing 53. So when you look at these, when you guys look at these little lines in here, so we're right here on this 400, but really to us this just means 0. We're pretending that it's on a 0, right? Each of these lines is going to be 10 knots of speed. So 10, 20, 30, 40. So then you can see there's 450 right there, but it's really just 50 for us. So that's 50. So we're going to 53 knots. So we first turned it to our wind speed here, or our wind direction, and then we're marking our speed, counting up from here, 10, 20, 30, 40, 50, and then it's just right above this at 53. We're just going to mark this right in here with a pencil. Okay, so that's marking that. Now, the next thing we're going to do is we're going to spin this to whatever our actual average heading is. So we're going to turn this to 320. That's our real heading. Yeah, let's spin this thing now. So there's 320 right there. So now what we do is now you can see that this dot now has rotated all the way around to where it's behind us. Okay, so now we take this dot and you move this dot, wherever this dot is, you move this to put it on the line where this currently is. So we move this up. We just put it on that line, the 00 line, which is 400 in this example. And now, wherever this dot now is going to be what our actual ground speed is for the flight. Okay? Now in this case, because you can see the location of this dot, it's almost directly behind us. That means the wind is coming from, it's pretty much almost a direct tailwind in this case. Now if you think about it, you can also think about it, like you can do this in your head really if you wanted to, because if you think wind coming from 150, I'm heading through 320, if you just flip that around and say, well, what's the, in a heading sense, what is the opposite of a 350 or 320? You know, just minus 180 from it, and you're going to get, I mean, it is 150, right? Or is it 160? Yeah, so 160. So you can tell just in that case, and then remember the wind is always opposite, it's where it's coming from. So the wind is actually blowing 330, right? Is where it's actually the direction it's blowing, but coming out of 150.
So that's exactly what that just did, is minus 150, or we can just minus 150.
180.
Sorry, that's what I meant to
180,
say.
yeah. From that, but that's only in the case that this just works because that just happens to be where the wind is.
Okay.
Now, if the wind was 270 and you're heading 320, that's not going to work as good. So you still would want to use this to do it, but you're going to, it works nicely in this case because you can quickly tell like 320, 150 is almost exactly 180 degrees behind us, but not exact in this case, but pretty much. So, and then you just simply move the dot to where your original circle, metal circle was, and then the metal circle now represents your ground speed. So in this case, this is just above 450, so it's pretty much a 53 in this case. So it's pretty much a 53 knot tailwind because it's almost directly blowing us from behind. So that is going to make, you know, the whole flight, you know, it's going to make it go faster. The wind is helping us. This, you know, the average wind in this case is helping us the entire flight. So we have an average tailwind on this flight of 53 knots, more or less. Now, like I said, this, because we're doing an average for the entire flight, being off a few knots or being off a few degrees on the wind direction or even the wind or your heading is not going to make a significant difference in your overall calculation. So that's why when I was trying to show you, like, however you come up with it, if you're off by 5 degrees, it's, we can even show examples of where we do this and then we move it 10 degrees and then do it again and see what the difference is. You're going to see it's not going to really be a difference. So, so I'm not too worried about you not getting it spot on, but you want to be in the general direction, from both where the wind's coming from and where you're heading. And then even this little dot, I mean, just because of the way, like, I write my circles so big, it's like plus or minus 4 knots either way, just even on that. So when you use an actual app and download it, it'll do all this for you, and it'll tell you tailwind 53 knots, or it'll tell you your new ground speed. But in this case, we have a 53 knot tailwind, and that's kind of how you figure it out. Cool. We're going to see this a lot more because right now we're doing a simplified fuel burn, which is for the entire route. Once we jump in and start dividing up the route into littler pieces, we're going to do this again on every individual piece for the final calculation. So we're kind of doing this like as one big whole, and then we segment the route up, and then we do it like 4 or 5 times just for one route, but in little pieces, and then we add all those together and then do it. So you'll see it a lot, but this is just the initial one. So I'll see if I can somehow show these guys how to do it. Okay, can you guys see this good here? I don't know if it helps. Is that upside down? That's probably upside down to you guys. Is that? I can't tell.
That's how we.
Okay. Let me see if I can lift this up a little bit better. Is that like even in good focus for you guys?
Yeah, it's in focus.
Okay, so what we do at the very beginning is we take this dot right here,
Okay.
and we trying to get this so I don't know if I can do it like this. Or even like this. Maybe this is easier. Is that harder to see there or easier?
It's actually better, a little bit.
It's better? Okay. So the first thing we do is we take this dot here,
Okay.
and we line it up on mine it's going to be 400, just right there in the middle. Like right on the numbers right there, if you can see that good, right there.
Oh, okay.
Okay, the next thing, so that's where you start. That's just basically your starting point. So then the next thing we do is we take this right here. So this right here is going to be the marker of where we align stuff with. So we're going to spin this thing to we're going to move this to 150. So what we're doing here in this case is we are starting off with our wind direction. That's the very first thing we're going to turn it to and mark. So our wind is 150 at 53 knots. So that is 150. So you're turning it to your wind direction first, just like that. Then we come down here back to where our little circle is, and each of these lines that go, so here's our starting point, but each of these lines represent 10 knots of speed. So we're going to mark our speed now. So we go 10, 20, 30, 40, 50, and then since it's 53, it's going to be just above this mark right here. basically where the 5 is, right on 450. So let's see if you can see that mark there.
Yep.
Okay. Now, so we've got the wind direction, we marked the wind speed. Now the only thing we're going to do is now we're going to switch this little index, the compass thing here on the top, to the direction that we are flying. So we're going to turn this to our average heading, which is 320. So I move that to 320. Okay. And now you can see that little dot that I made is now it's now down here. It's like directly behind the circle. So if you think about the circle representing the actual plane, that's what the circle represents, is the aircraft. That's where it's located. The wind now is behind us, coming from 150. So if you think about it, blowing in this direction. So it's blowing behind us at 53 knots and causing us to go that much faster. So what we do is we take this little dot now and we slide this thing up to that 400 marker where our circle, our metal circle, used to be. I always hate doing things backwards. So you see now how the dot now is on 400 where the circle used to be?
Oh, yes. I do.
There. Right there. So now if you go to where the circle is, that's going to represent how the aircraft speed, which is going to be, 453. So this is like a straight tailwind, but now, so if you move that dot to the 400 where this one used to be, that's going to make this one represent what the aircraft speed is going. So now we take whatever this one is, which is, it's nice because it worked out good in this example, but that's now 453, which means we started out at 400, now it's 453. So just do the subtraction, that's a 53 knot tailwind is what it's basically representing to us. So, yeah, you'll see this more, obviously, but hopefully that worked okay for now.
Yeah.
Okay, so now that part, so we've got our average heading, we got our average wind for the entire flight, and we've just figured out that our average wind component basically for the entire flight is an average of a 53 knot tailwind. So now we're going to circle back into this chart that we were looking at, which is not on that page. So now we're going to be looking at these charts called Simplified Flight Planning. So when you look through these charts, you're all going to have a copy of these, but all of these charts, there's a couple of different of these charts in here. And basically the big difference between them is the overall distance of the flight. So this one is for 100 to 500 mile flights. If we keep scrolling down, the next one is for 500 to 1,000 mile. So this one that we're doing is 1,048. So we're actually going to be even down on the next one, which is basically from 1,000 up to 2,200 mile flights. So we're going to be on the very, very edge of this one because we're just barely over 1,000. So that's the first thing we start with. We base whatever chart we're looking at is really ultimately based on the total distance of our flight. So that's the first thing you want to look at, total distance, 1,048. So we come in here. These charts to basically start making sense of these charts all have different little portions to them, but on these simplified charts, we start down here on the bottom left-hand corner is where we start here. And there's this thing right here that says ref line. That stands for the reference line, and that's basically where we start our calculation from. So all flights, every time we do this, you'll always start out right down here. Whatever your distance is, that's the first thing you go to, but you start out on this reference line. So if our trip was 1,200 miles, we would start out right here, but on this 0 reference line, or if it's 1,700 miles, we'd be over here. But it's always going to be somewhere along this 0 reference line, and just depending on what our distance is, we just match it up. So we basically are 1,050 miles. So since this is 1,000 and this is 1,100, we're basically starting right here in the middle. I'm going to zoom in on this. So we're starting, I'm going to sometimes the easiest thing to do is just even just put a line in here, or if you wanted to do one with a ruler, you can do that. But we're right here on the reference line, and that's just marking kind of up and down where that point is. The next thing we do is we adjust for the tailwind or the headwind of the flight. Now, we just went through all this process to figure out what the average wind was and then the average heading for the flight. We've ended up figuring out that this flight has a 50-knot tailwind is the average, or 53-knot tailwind is the average for this entire flight. So when you start looking at this, from right here at this point, we either move up or we move down for compensating for a headwind or a tailwind. So when you look at these figures on the side here, we're starting at 0. If you go up, it represents a headwind, which is -50, -100, or if you go down, it's a tailwind, which is +50, +100. Now, you can see that you have all these different lines in here that are contoured on these little angles, these arches. These represent the different, basically the contour lines for us to follow to compensate for our headwind. So if we know that we have a 53-knot tailwind for this flight, we know that we're obviously going to be down here somewhere because there's 50, so we're going to be just below the 50 mark. But when you go to the next point, you actually are going to follow the contour of these lines. So if we were going up, let's just go back and say, let's say we have a 100-knot headwind on this flight instead of a tailwind. We start right here at 0, wherever the trip distance equals. It's about 1,050. And then we go up to 100, but we stay at this point and we follow these lines. So if we're going up, we basically follow the line going this direction. Like I can't draw it down in here, but maybe that'll help right there. You can actually, it's not going to be a perfect arch because I'm drawing it on here, but you're actually following the line going this direction all the way up to where you get to 100. So that's, if we were going to 100, if I arched this line a little bit better just to make it this exact same contour as these other ones above and below it, then that would be, you can probably do a little bit of a better job with a pencil, but you're basically following this line on these same contours all the way up until you get to a 100-knot headwind, if that's what we had. So you would take it and it would take you all the way up to this point. So with a tailwind, we actually would be going the opposite way backwards and following those lines the same direction but going this way. So we would be essentially going down until we get to 50. So this is kind of a tough one because you actually have to go, you start here and you actually have to go back into the previous chart in order to get to it. because technically on the other one we're kind of like out in this range, right out in here, and then we're essentially drawing a line back to where we get to 50.
What? I'm sorry, you lost me there. I have no idea what you're talking about.
The other chart.
Yeah.
Oh, it didn't have it past the 50?
Well, you can see this one, the problem is with this one is that this one starts at 1,000.
Okay.
Okay, so
I was like, what?
yeah, I know it's
Okay.
confusing because of those two. So if that's why I showed you the example of this one, because if we have the 100 knot tailwind, then it just stays on this chart and it goes up here. Or if it was a 100 knot headwind, I should say. If it's a 53 knot tailwind, we go backwards the other way. But the problem is as soon as you get below 1,000 here, going this way, then it's technically back on to this chart. Because ultimately, if you think about it this way, a headwind, it's not increasing the distance of the flight, but it is increasing it, like from a fuel sense, right? It is increasing it because you have to fly. You have to burn more fuel to maintain the speed because you have 50 knots of wind, working against you on a headwind. On a tailwind, it's actually helping you. So if you're flying 400 and you got a 50 knot tailwind, your plane's really going 450, even though the plane thinks it's only going 400. So that's one thing that you kind of have to wrap your head around a little bit with aviation flying, is that all of us are used to driving vehicles that are attached to the ground. And if you're driving on the freeway, even if you have, and I know all of you have driven in conditions that have been really windy, right? Whether they be really windy from a headwind perspective or a tailwind perspective. But because you're attached to the ground and have wheels moving you, if your speedometer says you're going 80, even in a 50 knot headwind, if your speedometer says 80, you're really going 80. Like in real life, because you're attached to the ground, right? The thing is about an airplane, because it's not on the ground, it's in the air, the wind will literally, whatever the wind is a one-for-one, change off, essentially. So if you've got a 50 knot tailwind, it's going to increase your speed by 50 knots. If you got a 50 knot headwind, same thing, it's going to minus off 50 knots. So, it's easy to describe, but it's harder to wrap your head around when you're actually thinking about it, and you're actually trying to compensate for the wind and the fuel in your head. So it's like when you're on the ground going 80, but you can tell that it's really windy, like it's blowing against you. You have to really press on your gas in order to maintain 80, but you're still going 80. The wind is not slowing you down. The only thing you're doing is you're burning more fuel to maintain 80, but you're still really going 80. It's the same idea in a plane. They have to burn more fuel in a headwind, but it's also slowing them down one for one, whatever the speed is. So in this case, it's making the trip longer from a fuel perspective, or if it's a tailwind, it's making it shorter. So because this has a 50 knot tailwind, in fuel terms, it's really more like the flight from a fuel perspective is really more like 950 miles. Instead of being 1,050 miles. Does that make sense? Yeah.
So could you just minus off whatever the wind is? Could you minus that off of your speed? Like when you put in vectors 400, if you found out you have a 50 mile knot or a 50 knot, wind, could you put 350?
Not necessarily, because the wind, depending on what it is, if it's not a direct tailwind, and the other problem is too is with airplanes, they have, like, it's all based on power settings. So with an airplane, if we circle back again to something we kind of talked about more at the beginning of this class, we talked about indicated airspeed, true airspeed, different things like that. So when you're flying a plane from the power setting perspective, the only thing that it cares about is the indicated airspeed. That's all your airplane cares about. It doesn't care how fast the ground speed is. And there's so many different factors that contribute to an indicated airspeed. Like, for example, if you're flying at 10,000 feet through the air at 10,000 feet is a lot thicker and a lot more dense, and it requires a lot more fuel to fly through that air at 10,000 feet. Whereas if you're at 36,000 feet, the air is very thin, and you can go you can go through it a lot quicker. So if you are flying from Phoenix to Seattle at 10,000 feet, you're going to burn probably double the amount of fuel than flying at 36,000 feet. Even though it's the exact same distance, it's the difference between the air pressure. So you have the air pressure is one thing, then you have winds is a whole another ball game that's contributing to this. So from a plane perspective, when you go up to 36,000 feet, the plane really thinks that it's flying at about 250 nautical miles per hour, indicated airspeed. That's what the plane thinks, and that's kind of how it's based for its perspective and for its calculating perspective. But the ground speed is going to depend on the wind, the pressure, and all sorts of different things that have to be calculated in and then compensated. But if even though you're 36,000 feet and the plane thinks it's only going 250 miles an hour, it's really going 550 miles an hour because of the air pressure difference and the wind. Can adjust it either way, but it makes a huge difference. That's why, like, you hear like a plane like it only goes up to 250, but then how do they get these speeds where they say they're going 500 miles? It's like when the pilots do their announcements. Oh, we're going 550 miles. They'll always say across the ground. They'll always throw in these terms like, why do you got to say it that way? Like if you don't know otherwise and you're just a passenger that doesn't know anything about flying, like they always like specify it by saying, and sometimes they don't say the speed, but the ones that do, they'll always quantitate it by saying across the ground or ground speed, and because the speeds that they're actually looking at when they look in their cockpit, the thing only really shows them going 250. So anyway, so there's a lot of different speeds, basically, is what I'm getting at. But in order for us to correctly calculate the flight and the fuel and everything else, we have to know what the ground speed is. That's what's going to tell us how long the flight's going to take, and then the fuel and everything else is based on the ground speed because that compensates for the wind, the pressure, and everything else that we need to accurately calculate it. So with a 53 knot tailwind, it's helping us out. So even though we're still flying 1,050 miles on this flight, from a fuel perspective, it's really only going to take the equivalent of 950 miles of fuel. So we don't normally look at fuel in a sense of miles, but it's going to be the equivalent amount of fuel to actually fly 950 miles with no wind. Does that make sense? So on this chart, it's basically, and I know it's more confusing because it presses us back into the previous chart because of the distance factor. But now, after we've compensated for our tailwind, it's now bringing us back to right here. So at this next point, now that we've compensated for this is the next starting point or the next reference line that we're going to go from here, and we're going to go straight up.
There's a lot of these on my ADX too.
There is? Okay. We're going to go straight up to the altitude that we're flying at. So this first line right here says flight level 370 and above. So if we're 370 or above, we just go to this line. The next one, and I can zoom in so we can read these better. This next one says 350, 330, 310. So if we're at 340, it's going to be halfway in between 3.3 and 3.5. But we need to draw our line up from the simplified here, from this point here at the bottom where we ended up. We are basically, like I said, I'm just eyeballing most of this, but I'm just going to draw in a line right there that just connects. So we go from here and we go up to the altitude that we're flying at, which is 340, we already figured out. And on this scale, it's between the 3.3 and the 3.5. So from here, we take this and we go straight over So if you see here, there's another reference line. And so we draw a line from this point straight over to here. So I'll just connect them like that. I need to bring that one down a little bit. Oops. So once you get down to here, it's pretty easy. You just go straight up to your altitude. Once you get to your altitude, then you go straight over to this reference line. From this reference line, the only thing that we're going to compensate at this point is we're going to compensate for whatever our landing weight is. Going back to our weight and balance. Stupid thing reset. So
504.
What's that?
62,504.
Okay, so 62,504. So if you come down here along the bottom, we've got 50,000, 55, 60,000, 65. So if we're landing at 62,504, then so there's 61 right there, 62 right there. So we're going to be halfway in between those. I'm going to bring back my little line tool. So we start here on the reference line. So even if you wanted to draw like a line up from the bottom, just to like make it accurate for yourself, you can. But what we do from here is if we're going this way, like if we're landing below 60,000 feet or 60,000 pounds, sorry, then we follow the contour of this line backwards. If we're landing above 60,000 pounds, then we follow it to the right, going up. So we're landing at 62,500. Once again, I'm just like eyeballing and guesstimating it here, but I'm just going to draw it more or less into that spot. And I follow this line that has the dots. And then from there, if you go straight over to the right, that's what your simplified fuel burn is for the entire flight. And these have to be times by 1,000, but 7.6 would be 7,600 pounds. 8.0 would be 8,000 pounds of fuel. So we want to draw this line over. We can do that just to kind of signify where we're at. But 7.6, that's 8, so we're pretty much 7.9, more or less. That means that now that we've compensated for the wind and the temperature and our flight level, because we figured out our flight level, 340. We figured out that average tailwind or headwind. In this case, it was a tailwind, that negative 53 knot tailwind. And then we figured out that our climb out ISO temperature in Phoenix. That makes this flight burn, according to this, 7,900 pounds of fuel.
I lost you when you said if we land with more than 60,000 pounds, we're taking it up, and if we land. Oh, I get it now, because
from this line right here, this reference line, you're just simply going to your landing weight. So if your landing weight, if we were landing at, let's say our landing weight was 57,000, then all we're going to do is we go back, kind of like that headwind, tailwind part. You're just following it. If it's below 60, it's going to be going down to the left. If it's above 60, it's going to be going up to the right. It's kind of like the headwind, tailwind, just.
Well, so you just always automatically bring it to that center line from.
Yeah, that's the reference line. So,
okay.
So if you see this, it's kind of like the headwind, tailwind. It has that reference line. That's from this point, when you get to here, you got to come straight over to the reference line and then adjust for the landing weight. Either down to the left or up to the right. And then wherever you end on this, like if it was down to the left, then you would end like here, and then you'd go straight over from there, and that's your fuel. In this case, we went up to the right, to there, and then straight over. That's our total burn for the flight. So not to be confused with the total fuel. This doesn't include the reserve fuel, doesn't include alternates, doesn't include hold fuel, contingency fuel. This is just simply the burn from Phoenix to Seattle. So does anybody remember what we figured out was our burn? Like using the 4,000, 3,000 method? Just to compare these two numbers with each other.
So it would be 14,400 minus. So I think it was 11,900.
Okay, so pretty big difference, right? Mm-hmm. We figured 11,900 pounds. That was based on flying, based on that 4,003. So this is a pretty big difference. So we are at 11.9 and we're at 7.9.
That's kind of scary.
Now this is the thing is anytime you have a tailwind,
right.
It's because it's a tailwind. So when we do the 4,000, 3,000, that's not based on any winds at all. So that's what's really making this a big, like if this flight had a little bit of a headwind, that 4,000, 3,000 rule thing that we use, like I said at the beginning, is an overestimation. Right? So if anything, we always want to overestimate. We never want it under. So that's always going to be heavy for sure. So the simplified is actually taking into consideration those other variables. Especially the wind is the big part. So
is this the number that we're supposed to put on the dispatch release?
Not yet. This is simply level 2 of your fuel. The one that we put on the dispatch release at the end is so we're going to go back through and do this similar process, except we're going to divide the route up. This is kind of just that estimation.
So this is the average for Phoenix to Seattle. Now we're going to redo it from Phoenix to that first point, and then.
Well, we're going to do it. We'll go back and that's not exactly how we're going to divide it up. We'll divide this flight up into like 4 segments. There's going to be our climb out portion. That is when we take off from Phoenix, climb all the way up to 34,000 feet. We're going to get that fuel. We don't use winds actually on that portion at all, but I'll show you how to figure that out. That's coming up later. And then from that point, the en route section. So we have climb out, en route, descent. Those are going to be your 3 basically sections of your flight. The en route portion alone might actually be subdivided 2 or 3 different times depending on how long it is, because we're going to break that up and figure out the wind on, we're going to break it up into like anywhere from like 100 to 250 mile sections and then calculate those independently. And then we end up adding that all up on the fuel and then using that as our final fuel. So the only thing that we have done to this point is obviously we've done all the steps that we went through, last week. We got all the way up through the weight and balance. We did the initial estimate, the 4,000, 3,000. That was the numbers that we used to get to this point. Today, we have the only thing we've really done now is we're refining the fuel. And that's kind of the key thing here is we're taking more variables into consideration, the winds, the temperature, and our flight level. That's what we basically just did in this situation.
Are we putting these numbers anywhere on our flight plan?
Not yet, no. I mean, this is all, if you were doing all this, in a section, you're going to have, your initial fuel estimate section and then your simplified fuel section. There is a spot for this to put it in here.
So why do we do this if we don't? What was the point of this?
The reason we do this is because this is going to be what we actually use to figure out the fuel that we want to take with us on the flight. See, the problem with when you do manual flight planning is that you don't necessarily know the real fuel until you've gone all the way through and calculated it all the way through to the end. And so the problem is that you don't know where to start. as far as a fuel number, right? We have a fuel number that we use to do the weight and balance. That was just that 4,000, 3,000. We have to have some sort of something to go off of in order to do anything to begin with, and that's what that gives us. The simplified fuel just gives us a better idea of what the flight's really going to burn as an overall average. And then when we get done with the simplified fuel like we have now, what we do is we take that number and we compare it against the initial fuel estimate. And we look at what the difference is. Now in this case, it's a pretty big difference. Normally, on most flights, it's not that big of a difference. Normally, if you ask Christy, she's probably done several of them, but normally it's not this big of a difference. This is a little bit more dramatic because it's a 50 knot tailwind for the entire flight. So that's really knocking off a lot of fuel for us that we don't have to use. So what we do though is we take that initial fuel estimate that we came up with, and then we take the simplified estimate. And then we kind of see what the difference is between those. So if the initial estimate is larger than the simplified, like it is in this case, we split the difference between those two, and then that's the number that we use to take with us. Now, in the case that the simplified fuel is more than the initial, then you just simply go with whatever the simplified is completely, because this is the more accurate fuel. Now, even though in this case it's saying that we need a lot less than what we estimated, just to be safe, we still want to go with a little, just in case, like I was telling you about the winds aloft, they're not 100%. And even when we're doing our heading, we may not be exact, those aren't, it's not a perfect science in manual. Manual flight planning is not in any way, shape, or form meant to be exact. And so that's kind of the whole point of it. But we have to kind of have something to go off of, and we always will lean, on the cautious side with anything in aviation. So if simplified is less than the initial estimate, then we just, whatever the difference is between those two, just split the difference and then go with that. If simplified is more than the initial, then just purely take whatever simplified is and just throw out the initial one. So what's the difference? So 11.9 and 7.9 is the difference?
Yeah, 11,900.
So 4,000 pounds of fuel. So add 2,000. And so we were 7.9, so we'll just plan this flight at 9.9, so 9,900. Now we're not going to go back and redo the weight and balance, okay? In this case, the weight and balance is, the weight and balance portion is technically heavier than it should be, which is what it normally is. Like in real life, in dispatch, like when we're doing real releases and we send them out, all of our stuff is based off of estimation. So this is kind of the same way it works in dispatch, although we have computers doing all these calculations, instead of us doing it manually. It still is using an estimation of the total flight. Like for instance, like when I'm starting a flight, I'll hit a button and it'll tell me how many passengers are on the flight. Okay, so if let's say there's 70 people. Okay, I don't know how many of those are kids. It just is going to take, like my software is just going to assume that they're all adults. So that's already going to be probably heavier than it should be, right? 70, and I'm just assuming no kids. So then the next thing I look at, the next thing it automatically calculates with that is it calculates bags. And my software at work just assumes one bag for every person. So we don't actually get a bag number in dispatch. It just, if it's 70 people, it's going to plan 70 bags. That's usually heavier than what it ends up being. Some flights are more, like if you're going to like a ski market and the people have all these skis and things like that. Sometimes it's heavier, or Mexico flights always seem to be heavier than what we plan, but those are kind of the exceptions to the rule. So most cases though, if you have 70 people, usually 75% is going to be the bag number, more or less, from what I've seen. So like a bag number of like 50 would be really more true life accurate for if you have 70 passengers. But we plan 70 bags. So now once again, we're a little bit heavier. Then we plan the flight to fly exactly as it says. You know, like the SID, the star, like we assume that the plane does not veer off of that route. It gets no shortcuts from ATC. It does everything exactly as we say it's going to. And however, they almost never do. Never. Almost every single flight that we have will get little shortcuts. Or they'll skip this one and they'll go direct to this one. Instead of going clear out here 20 miles, we skip that. So now they just cut down 40 miles. But our planning says, and we have to plan it as if they're really going to fly the entire route. So now once again, we're higher than what it probably will end up being. The winds aren't exact. They're using the exact same winds aloft that I just pulled up as if it were a real flight. They're using those winds, and those winds aren't always perfect either. So you get all of these things that add up into the end that, you know, if I say a flight can take, if I think a flight's going to be really close to like max takeoff weight based on what I planned in dispatch, usually once the captain, and Andrea could probably speak to this a little bit. She probably runs into these issues. Yeah. A lot of times, like the dispatch for release will think that the flight's going to be weight restricted. Like if it's right up against max takeoff weight and it thinks that we're going to maybe have to bump people because we're going to be overweight. But then when the crew gets in the plane, the flight attendant does her true count of like kids, adults, and then the rampers do the actual cargo load report. Okay, we got this many bags. And it all ends up being less than what we just planned. And then we find out we're really 500 pounds under max. And now we can take everybody. So there's always a lot of things that end up just changing based on what the crew's actual numbers end up being at the time of departure when they do the real weight and balance. So hopefully that explains it a little bit. We're just always heavier than what it normally is. So. Okay, so in this case, we are going to go with 9,900. We're not going to go back and change the release, or sorry. Well, it's 7.9, but we're splitting the difference, remember?
Oh, right.
So now to plan like what we're going to go with, we're going to plan 9,900. So I'm going to bring the release, or sorry, the flight plan packet back up. All of these numbers that we just planned and talked about, they all go in this section right here, Simplified Flight Planning. Now, we're going to actually put what we really came up with in this box here. So in this one, we're going to put 7,900. This isn't necessarily stating the fuel that we're going to use. 7,900, though, is what we would plan. We don't have an alternate. So that's 0. We didn't plan no contingency fuel. Then this is going to equal our takeoff fuel. So whatever 79 plus 2,500 is.
10,400.
That's going to be our takeoff fuel. And then 10,650 is going to be our ramp fuel. Now, when you're looking at this ramp fuel and this takeoff fuel number, the only thing that dispatchers care about is the takeoff fuel number, okay? The takeoff fuel number represents the flight as it takes the runway and gets ready to take off. Those are the numbers we care about. We don't care about the fuel that the plane burns pushing back from the gate and taxiing out to the runway because that's not in the air. So we always, in this class, we always just plan 250 pounds of taxi fuel But for our purposes, like the weight and balance is an example to use here, because the weight and balance doesn't care about the taxi fuel. The weight and balance only cares about what the fuel is as the plane is rolling down the runway, because that's where the real weight is, right? Any fuel that burned prior to taking the runway, it doesn't matter because it's not on the plane anymore. So don't confuse this ramp fuel number with takeoff fuel number. The takeoff fuel is the one that's important to us.
How many pounds of fuel is a gallon of fuel?
6.7. So yeah, a lot of gallons.
Yeah.
So 10,650. Now this next part down here is going to be all of the numbers that we just came up with, except it's going to be converted in a time sense. So if we fly, let's see, so if we're at 7,900, going back to our sky vector, so we have our total route distance. So in here we're just basically putting our ETA, the flight ETA into this column down here. This is basically telling us what do we have on board as far as how it represents as far as like minutes and time. So like 2,500 pounds of reserve right here equals 45 minutes of flying. That's all that this is doing. It's just converting our fuel to a time element to say, like, so a pilot would know, well, if I've got 7,900 pounds of fuel, that's the equivalent of 3 hours and whatever. What was our ETE that we came up with, our estimated time en route?
I put 338, but when you did it on vector, it was like 342, 341.
348.
A couple minutes more.
Okay.
When we did it the first day, we came up with 338.
Yeah, I noticed that, like, when we were planning routes, we'll plan the exact same route and mine will be longer. By like a few minutes.
And it's all like distance-wise or time-wise?
Time-wise.
Time-wise? Time-wise will be because...
Wasn't that because you had a taxi time, a 10-minute taxi time?
No, my ETE was like 25 minutes less or more than yours.
Yeah, I'm pretty sure when we did this the first day, it was 3 hours, 38 minutes, which put an ETA at 428.
Yeah, and it would be when you do your initial fuel, when you're doing the 4,000, 3,000, it's not compensating for anything. It's not compensating for the altitude or any of those things or the wind. So now with this, one thing you can plug in is you when you're doing your initial one, you can plug in that 400 number up here. So were you plugging that in on yours, Aubrey? When you were saying, yeah. Okay.
Yeah, it was only off by like, it was less than 20 minutes that it was off. It was the same route. I don't know.
For some reason, see this one, how it's doing this little jog right here? Sometimes it'll do weird little things like that. Caddy. See that? How it added caddy in there?
Yeah.
That's weird. That's Dovey. That's caddy. If you just right click, let's see. Delete. Yeah, instead of having caddy, or it took out Beatty instead. That's really weird. Yeah, I don't know why I did that. That's another thing you gotta be careful with SkyVector. I mean, that only did that because I deleted it and put it back in, but it was fine before that. But the other thing is here is once you know your altitude that you're gonna fly at, you can plug it in right here. That's good. That's going to change. The only problem though is that the thing is on SkyVector is you can never like perfectly go off of what it says on this ETE. The reason why is because SkyVector thinks and it uses real-time weather, and so it thinks that you're wanting to fly this flight here in like an hour or two, right? And so it's taking the current winds aloft and plugging it in there.
Maybe that's why.
It could be.
That makes sense.
It could be. Yeah, it could be if it was just the ETE that was different, right? Not the distance.
I can't remember. I just remember the ETE being different.
Yeah, if it's ETE, then it's usually just because of the wind difference. So ETE 250, yeah. So Christy was asking me the same question, like on the break. Like she was getting a little bit different. Like, see, if I take out 340, look what it changes to.
Yeah, that's
343. The difference there is that it thinks that you're flying at like 100 feet instead of 34,000 feet. That's going to be it. SkyVector will go in and it'll calculate your winds for you. And so you have to be careful, because if you get a weather packet that's from yesterday, and it's using today's stuff, so it can change. Or in a lot of cases, if I'm using a weather packet from a couple of months ago that we're just doing the same flight as like maybe the last class did, then yeah, you're talking weather from like 3 months ago. So so you got to make sure that this is only, SkyVector is only meant like in its complete, I mean, it's helpful, but you have to know that it's really not, it's not where we're ultimately going to get. Like the only thing that's honestly perfectly reliable is the distance. The distance. That's about the only thing that you can really say that that's going to be spot on. And that's just making sure, even the distance, you got to make sure you got your whole SID and your whole star. Otherwise, it will be wrong, and that it can even mess up, as you've seen. So, other than that, the estimated time en route might differ by a few minutes. They've got a lot of features in SkyVector, but because we're not using real-time weather and things like that, and it also doesn't know, even when you plug in, like we're using 400 here, right? But the truth is we're really doing 453 now because of our tailwind, and that's the average, and then we're really up at 340. So that's taking us down really 234. But that's, even at that though, it's still using different wind, right? So it might not be perfect. So the only thing that's reliable is plugging in your route, getting the distance. Anything else is, you can use the 400 speed in there to help you on your distance, but that's because you're manipulating it. So, but even at that, you might have the different winds. So you still probably need to always take that 400 and divide it by the 148.5 or the 1048.5 to make sure that it's not adding or decreasing time because of the current winds. So anyway, so back into here, this is basically putting in our estimated time to the destination and then figuring, if there's no alternate, there's no contingency, and then you're just plugging in the total time in fuel that the plane has on board. That's all you're really doing. That's all you really do with the Simplified. It's just those two columns.
So are we taking the time that we came up with, or we're converting the burn to time?
So right now, the best way to do it is if on the simplified version, how you want to calculate the time, I should put my calculator in there, is take that total speed that we ended up coming up with, because our initial was based off of 400, right? This one, now that we know we have a 53 knot tailwind, you can base it off of 453. So other than that, though, you want to still take your distance, 1048.5, and divide it now instead by 453. And now you still have to do your conversion, so your 0.31, into the 60 minutes. So it's 2.314 hours. And then we just have to convert that 60 times 0.314. So it's really 18.8. So just say 19 minutes. So 2 hours and 19 minutes. Based on the simplified planning, that's what we came up with. So you can just write 2 hours, 19. You can even just go 2H19M if you want. And then 2 hours, 19 minutes plus the 45. So we didn't have any alternate or contingency. Ends up being
3 hours and 4 minutes.
3H04M. So that's all you do there. It should be pretty simple. You guys need a break for a second?
Let's do it.
Yeah.
Real quick, so like all 4 of mine on the dispatch release, I was filling out, like putting in what Sky Vector was giving us. So basically we'd probably go through and get the actual, same with the fuel, like the 14,400, we'll have to redo that.
No, well, see, that's the thing. If you're talking about your front page, you shouldn't be filling out any of that on the front page yet.
Okay.
Yeah,
The fuel?
on the front page.
Like this actual dispatch release one?
Yeah, so remember the front page is reserved. Like none of this gets filled out until you are done with your flight plan, like all the way done. So none of this, all of those fuel estimates, this ends up being your final fuel that we do at the very, very end, like that we come up with. What's that? The route? So yeah, none of this would get filled out yet. This we basically, most of this we fill out once we're done completely. This is the last thing we usually fill out at the very end. Other than, MELs you can put, if it's things are not going to change, like MELs not applicable, the only other things that are for sure is the date, the aircraft number, the city pair, the IFR. This simple stuff that we put in, flight number 1, that stuff, yes. The only other thing that we've added in here that we could put in is 340 right there for 34,000 feet. But anything else, even ETE, ETA, all this stuff is still not known perfectly for sure until we get done doing the final part.
What about the route? Can we throw that in there?
Yeah, the route you could put in now at this point. But anything fuel related won't be figured out till the end.
Yeah, for like runway and stuff like that.
Yeah, if we've got this stuff, you can plug that in. But the easiest thing though still is to just leave the front page alone until you're done. Honestly, there's no point really even in plugging in onesies and twosies, worth of stuff when you can just do it at the very end. I just like to just leave it all for the very end just to make sure everything's correct. Because there's usually spots for everything else in the rest of the form here. Okay, did you guys need a break for a minute? Anybody?
Let's just end earlier.
Put our break at the end.
We're at least going to run through another one. So I want to take at least one more of the ones that you guys had from last week and run through doing the simplified portion. It takes a lot longer running through it the first time. The more we start running through it, the quicker you'll see how you can hurry and get the information and plug it in. So does anybody want to give me the information from one of their other flights?
Is this where we're stopping on this one then? Is that what you're
Yeah,
saying?
today's objective is to get through the Simplified. Okay. The rest of most of this week is really going to be you taking the flight plans you've already done and getting them now to this point.
Well, are we not gonna go over any that have like MELs and alternates and stuff like that?
No, we'll start adding once we get complete. Once we get these ones all the way finished, then you're going to start. You'll be doing ones just from scratch with MELs, weather, because we already have. I mean, these ones are already assigned the weather, the MELs, and everything else. So, but yeah, we'll be adding those in. But I want to make sure you guys have all the steps in before we start throwing MELs and stuff like that into it. So does anybody have one of the other ones handy?
Yeah.
Denver to LA.
Okay.
Or should I just do it?
What was the Sacramento one too?
Yeah, Sacramento, Helena.
Okay.
And then we had San Diego and Salt Lake City.
Okay. Okay. We'll do Denver, LA. Just bring up another one of these. Okay. So what was the total fuel for Denver, LA that you guys had? I know you guys might have it a little bit different, but based on your routes and stuff.
I had 9,900.
Okay, let's just compare it. What'd you have?
Mine was a lot more than that. It was 11,600.
Okay. What was yours? Same?
That's what I had. So,
My route was probably different.
Yeah.
What'd you guys get? The 12 fuel? I had 11.7.
11.7, 11.6. What'd you guys have? Tyler? You had 99, right?
Yeah, I had 99.
John? 11.5?
Right.
Okay.
Maybe I missed the 2,500, but I don't know.
Maybe.
My
Well,
route's pretty simple.
sounds like 11.5, 11.6. I mean, we'll just go with somewhere in there. We'll just say 11.6. Split it. All right. So, okay. So we're saying 11,600 is your release fuel for Denver to LA. Okay. So bring up that packet. The computer is running crazy slow right now.
You're giving me for you guys, Jared, and I forgot I still have to shower. Shower early.
Okay, so start looking at this. First thing we're going to look at is let's get our ISA number for Denver. So remember, the big things that we want to figure out are going to be our altitude capability for the flight, our ISA number for takeoff, and then figure out just our winds for the flight. And then take those averages, plug them into that flow chart, figure out a fuel. That's really all we're trying to do, start to finish for today's stuff. So it's 11 degrees in Denver, Celsius. Denver airport is roughly 5,400 feet above sea level. Save us some time from looking it up. So based on the ISA calculation, does anybody want to make a stab at figuring out the ISA deviation that we have here for Denver? It's 5,400 feet.
About 1.5.
Yeah, so if we're at 5,000 feet above sea level, what should it be if it's ISA? If it's following standard ISA lapse rate? So just, times it by, it should be negative. It should be 5 degrees Celsius, just 2 degrees per 1,000 feet. So we're 5,000 feet times 2, 10 degrees, right? So minus that off of our 15, it should be 5. And then we're at 54, maybe minus off 1 more degree, so maybe 4 degrees, because we're kind of halfway between 5 and 6. So 4 degrees Celsius, it's 11. So we are ISA plus 7, which we would end up rounding to ISA plus 10, because we go ISA plus 5, ISA plus 10. So ISA plus 10 is where we're sitting in Denver. Okay, so we got that. That's figured out. What was your guys' takeoff weight on your weight and balance?
71,013.
Everybody pretty similar to that?
71,113.
Yeah.
71013.
Mine was a little less, but I 69, 3, 1.
Okay, but everyone else in the 71 range? Okay, that works then. So what we're going to do is we're going to go back up to our trusty altitude capability chart. Right here. Okay. I'm gonna get rid of that one. Okay, so 71. Okay. So we'll just say that it's
only 71,013. So it's like closest to 71.
Okay. So in this case though, since we always go a little bit heavier, we'll go so that's 71 right there, so we'll go like 71.5 right here. And then we're at ISA plus 10 and below. So we technically are going to go up to that line. And we're following from this line. So I'm going to back out a little bit here. Go from there straight up to there. Okay. Now, if we're on that line, now we can figure out right here where we're at. So right here, we just go straight to the left, and we can see that we can almost get to 39,000 feet, but not quite. Okay. So this is Denver to LA, so we've got to be even or odd? Even. So if we are basically capable of getting up to 38,500 feet, that means we would just go down to 38. So 38,000 is what we'll plan it at. So now we've got our altitude. Outside of that, there was nothing else restricting us. We don't have any MELs, so we know we're good for 38,000. Temperature, altitude, we've got 2 of the 3 things we need. Only other thing is going to be the route, or the route and the winds, yeah. But the route will help you decide which winds we're going to use. So what was your guys' routes? Were they mostly?
For the information that you've been doing it off of so far, the route for that was Rocky 3, EBL, J60, Hector, and
Down to Daggett, right? Or to,
No,
to Hector. Okay, yeah. Red Table, J6 to Hector, and then the Downey 4. Okay. Then maybe it was just the reserve fuel or something. Okay. So let me hurry and gather our winds aloft. I'm going to get rid of all this information. See, I'll just bring this back here for a second and then just copy and paste it.
When you planned it out, did you change the speed and anything?
Did you guys? Mm-hmm. Yeah, that's weird. I think I did 400. Maybe it was crazy to go back.
Okay. There's our winds aloft. Denver, Grand Junction, Bryce Canyon, Vegas, and Ontario. Those are the ones that are basically closest to along the route. So, so we're at 38,000 feet. So you can see just below 39, which is going to be the closest one. So the biggest thing here is just comparing the last two. So that's 240 and that's 240 on the heading. So that's easy just to keep at 240. 23 and 24. If somebody wants to be adding these up as we go along, then we can just quickly get the average. So 240 is going to be the average on the first one. So the next one's going to be an average of 230 and 240, so just do 235. And the next one's going to be 230. The next one's going to be 235. and then 235, and then divide by 5.
235.
I figured they're all pretty much the same. So, okay, so 235 is going to be our average wind direction. As far as our temperatures go, or sorry, our wind speed goes, 73 and 87. Let's see, so it's going up. Let's see, so it's a difference of 5,000 feet, and that's a difference of 14. So we're going to be more like 85, 80s. So 80, we'll just plan like 80, I'll just plan 85. So 85 plus 90 plus, and all I'm doing, just so you guys know when we're looking at this, all I'm doing is I'm just looking at this number and this number, and we're obviously closer to 39 than we are 34. So I'm just I'm just taking a few off, yeah. And I'm not trying to like make this like where you got to go do some calculation. I'm just take a few off in your head. Like I said, this is the part that getting it like right down to the T is going to make maybe like a pound of difference on your fuel. It's not going to make a significant difference. So don't sit there and beat your head on the table doing senseless math. Like, you know what I'm saying? Like, this is a time waster if we really start digging into it too much.
So should we just add those ones and then take fuel at the end? To test.
Yeah, I mean, that would probably be fine. Yeah, honestly.
Okay, so what are they?
So 87, 94, 96, 94, and 80. And then maybe like take off like.
So it's 451. So maybe do like 440.
Let's go with 440.
440.
Yeah, divide by 5.
88.
Seems reasonable. Okay, so down here, I'm gonna mark these off. So average wind heading 235 at 88 knots. Okay. Clear that out. Go in. So that's saying average heading of 238. Oh, this is going to work out really nicely. Average heading for the flight is 238. So you can assume, I mean, you probably don't even need to use this in this case. It's so close that it's going to be, yeah, this is going to end up being really an 85, 86, 87 knot headwind straight on, right? So anytime these numbers match, just remember the rule of the wind since it's opposite. If these numbers match, that means you're flying into the wind. Just like on a runway, if you're picking a runway to land on, you pick the one that matches the wind, right? So, so 88 knot headwind essentially on this flight. So I'm just going to throw it on here for the sake of throwing it on here. Our wind direction is 235. For those of you online, I'm just doing that little that wheel, the whiz wheel, that's what we call it. Little spinny thing that I attempted to show you. So you use that like app thing, 87.9. Cool. So yeah, I mean, that's what we assumed, right? 88 pretty much. So 235, 10, 20, 30, 40, 50, 60, 70, 88. Okay. And heading of 238 right there. So now when in this case, because when I move the the wind speed, I only moved it like 3 degrees over to get my heading, so now you can still see it staying there. Now in this case, when it's a headwind, you're still taking this dot and putting it where this one is. So you're sliding that down and putting it on the 400, and this is still representing your ground speed. So now obviously it's the other way. It's a ground speed of like 312. What is that? Did that give you a ground speed?
No.
Well, it did, I guess it didn't because you don't put in a true airspeed. So if we're doing 400, then it's 312. We don't care what the speed is here. All we care about is the math. 400 minus 312 is 88. That's all we're trying to get at. So regardless of what the true speed is, that's all that really matters. So 238. Okay. 88 knot headwind. So let's go to our simplified. What was your guys' total distance on this trip?
Let's see.
You know what? I don't think I wrote it down.
I can hurry and plug it in.
I had 757.3.
757.3?
Yep.
Whoa.
It's not with the 4 down feeds, just with the 4.
Just with the.
I don't know if it makes a difference, but J60, not 6.
Oh. Yeah.
J146.
Oh,
Well, that's not what I have.
J60.
J60,
Yeah,
we put.
And we didn't put the APU.
I did not go to Albuquerque.
Yeah. Well, yeah. J6 took it to Albuquerque. That's the problem. That's what it should look like.
Much better.
Okay.
No, that's how I did my problems the other way.
Albuquerque.
So 810.3
Just
on that
stop
one.
there.
Okay.
Albuquerque.
So going back to this chart. So that's the 100 to 500. This is the 500 to 1,000. So that's the one we want. Get rid of that previous line crap we had in there. Delete it all. Delete. Okay. So 810.3. So remember, we start on the reference line. Go straight over to where our distance is. So this is 800. So we're 810. So that's 810, 20, 30, 40, 50, 60. So that's 850 there. So these are all 10 miles on each of these dashes here. So let's zoom in. So this is going to be nice because we can keep it all on one chart here. Got to get rid of that one. Okay. So 810, we're right here, and we have an 88 knot headwind. Who knows, it might actually take us into the next chart. So anyway, it's nice because this line is really close. So we're really just following right along the bottom of this line and just tracing it until we hit 88. So we're just barely below it. So it's like literally like right underneath it. So right here we're at 50. Right here we're at 60. Right here we're at 70. Right here we're at 80. So we're going to be like 80, like just below 90, which is, going to be clear over here. Unfortunately, we do go into the next stupid chart. Get rid of this crap. Okay. So 90, it's right there, so it's like right here. It's going to pretend that we just came through the other one. Anyway, so like right there. Perfect. Okay. So now we are going to take this line straight up, and we are at 370 and above. We're at 38,000 feet, so we're going to go to this line that just says 370 and above. So we are just inside of that line right there. Take it down to right there. Okay, and so that one is just going to be just under this line. So I'm going to like just trace it from right here. If you have rulers and stuff to use, it'd be great when you do these manually. But anyway, so I'm taking that line and I'm just going straight over to that reference line. Now I'm here at the reference line, and what was your guys' landing weight? 61,913. So 62, basically. 60.
I had 68,513.
Oh, 60. Because what are you guys coming up with total burn, more or less? 89.50. Because total fuel was 11.6, right? So minus the 25. So somewhere in that ballpark. 91 for you. So we're talking anywhere 88, 89, 9,000, somewhere in that ballpark. Okay. So let's just say it's 9,000. So what's your 72 or minus 9? So 60, basically 62,000 pounds. If we round it up a little bit. So we'll just say 70 or 62,000 is our landing weight. So it's going to be just up. So here's 61, here's 62. We're following that contour.
Let's see your mouse one.
Right here.
Oh, okay.
So right there, we're actually pretty much right on that line there. So, kind of hard to see, but it's basically right there. And then from there, straight over. 8.1 maybe, if we round it up. It is above 8, so we'll just say 8.1. So 8,100. So in this case, it's still, Simplified is still even less than the initial, even with an 88 knot headwind. So closer though, it's not 4,000 pounds different like the other one was. But you'll almost always find that Simplified is always usually going to be less. There's very few cases where it's more, but anyway, so split the difference, 8.1 and 9. So we're going to basically add maybe 500 or 600 pounds and call this 8.6 is what we would use. So that's kind of the process there.
That was much easier the second time.
Yeah, and it does go a lot faster. It's just that calculating of running through the calculations and talking about ISA, all that crap that boggles it down.
What was that last 500 you threw on that?
So once we get done and we know what the simplified estimate is, in this case 8.1, and we know what the initial one that you already had was, that was split the difference. So I added.
We had 810 miles total distance and we came out with 8,100 pounds.
Yeah. So is that a little bit easier? Yeah, I mean, the thing is most of this stuff is like this. It's a lot to talk about, it's a lot to run through, but the more you cycle it, the easier it becomes. And the thing is that's kind of nice about these is that the way you're calculating those winds and figuring out the heading and the wind, it's going to relate and help a lot with when you do the individual segments when we get to the next phase of just narrowing it down a little bit even further. There's obviously more things to add in, but it becomes a lot quicker. So, but everything the first time you see it is mind-numbing and senseless. And the nice thing about all of this is you only got to do this one time. And as soon as you guys pass your practical, you can forget anything that you ever learned about this stuff, because you will never, ever do any of this again. As far as manual flight planning goes, don't forget the 1, 2, 3 rule, things like that.
That's the one thing we're learning from this whole course.
1, 2, 3 rules.
Yeah.
So one thing that sticks.
There's all this stuff that you need to take and pass with, but once you get that certificate, clean slate.
That's why we go through school again. Because it's like,
It is. Well, the thing is you get to the airlines and all of their stuff is, it's not that it's different. There's a lot of stuff that is got to be the same, but there's also stuff that where they do things differently. You know, I mean, manual flight planning is a one-time thing. It's you got to know it to get your license, and then you'll never use it again. So that's it for today. Unless you guys want more, but if not, feel free to leave 18 minutes early. Thank you,
Those
guys.
charts are going to be in the flight planning.
yeah, like a simplified chart.
Yeah, I'm gonna post that whole page of it in there. So all of the charts.
And then, so now for the ones that we're doing